A knowledge graph is a data model that represents knowledge as nodes connected by relational edges and properties that can be defined for both nodes and edges. Knowledge graphs have become an industry standard due to their schema flexibility, ability to integrate data across multiple domains, and inherently semantic encodings. They can be a rich data structure for storing complex relationships, are human and machine readable, and can support complex data analysis and AI tasks. Even though KGs are popular for modern day applications, the role of visualization and visual analytics for KGs in practice is unclear, since there's no design space for KG visualizations, and we aren't sure how KG visualizations might differ from normal graph visualizations. Other examples of unknowns include: who are the typical users of KGs? How do their expertise, pain points, or tasks differ depending on their roles? What visualization solutions currently work for KGs, and what is missing from the landscape of visualization research? To address these questions, we conducted interviews with 19 knowledge graph practitioners to identify critical challenges that could be alleviated through visualization design. The 19 participants we interviewed come from a variety of domains and companies and have different levels of expertise with creating, analyzing, and visualizing KGs. You can refer to our full paper for the details. We'll now discuss the interview protocol for our study. You can follow the QR code to view our codebook and interview material. We spent roughly 1 hour interviewing each participant. After the interviews, we qualitatively coded our interview data and conducted a thematic analysis to organize the findings into 4 high-level themes. We categorized the codes into the use cases for why participants use KGs over other data structures, the tools that they use with KGs, challenges in general they face, and any of their visualization needs. We're now going to discuss the findings of our interview study. We asked our participants why they use a KG instead of another data structure. The first main reason is that KGs have a flexible schema. If you want to add any kind of node, relation, or property to the graph, it's easy to do so and doesn't require necessarily creating new tables or new columns in tables to represent the new data. The second is that KGs can easily integrate data across different domains, for example, to connect diseases with treatments or manufacturing data with financial data. The third is semantic encodings. The relational encodings in KGs have intrinsic semantic meaning that can help users better understand their data and improve data analysis. Our participants use KGs for a wide variety of use cases. These include connecting cyber vulnerabilities with threats and operating systems, connecting events that trigger downstream user workflows, connecting diseases with genes and treatments, and discovering new material synthesis processes. Other participants use KGs for data cataloging to create a shared queryable knowledge base or to standardize terminology across a large enterprise. People also use KGs for anomaly detection as well as stock prediction. In our analysis, we found 3 primary personas among our participants. First are KG builders, who create the KG from the source data. They select their KG representation method or database, parse the input data, and ultimately build the KG. 12 of our participants fall into this persona. The second is the KG analyst, who queries the KG to train models, discover new insights, or create actionable reports. 17 of our participants would be considered analysts. Here we note that one person can fall into multiple personas. For example, many of our builders are naturally also analysts. The third is the KG consumer, who is usually a domain expert or stakeholder who takes actions based on insights generated from the KG, but may not necessarily have the skills to directly query the KG. Only 2 of our participants are consumers. These personas have different tasks and different needs that we will discuss later. Moving on to the challenges that our participants face. Some challenges are not specific to KGs. For example, 15 of our participants reported challenges with data quality, whether with sparse, incorrect, or out-of-date data. Our participants also had trouble manually entering or validating data at the scale of thousands, millions, and billions of nodes. More specific to graphs, our participants had challenges with entity disambiguation, which involves detecting nodes or links that are duplicated in the graph but should really be merged into one. And also they had problems with what we call choke points, or nodes that are so densely connected that they can artificially inflate the number of paths returned in a pathfinding algorithm and lead to a lot of noisy paths to sift through. Another important challenge our participants faced is with querying. This is challenging not only because learning a querying language can be difficult, but also because different graph representations systems can have different querying languages. So even if a user learns, for example, Cypher, that might not help them learn how to query a different system with Sparkle. Also, many querying systems don't offer interim results, and users can end up waiting many minutes for a slow or empty query that really disrupts their workflow. A final challenge we'll talk about is again not specific to KGs, but are these socio-technical challenges. Our participants have noted challenges with KG practitioners not fully understanding user needs or over-focusing on technical implementations at the expense of end-user benefits or other organizational challenges of implementing KGs in practice. For example, this is a quote from one of our participants. People always want to go build a knowledge graph of everything. They've defined success from a technical point of view, but then what are you going to do with it? Why are you doing it? Who's going to use it, and what's the value that it's going to produce? Although node link diagrams are known to have issues with scalability and readability, we still found that they were by far the most common graph visualization technique used by builders and for communicating KGs to end users. Builders, for example, often use node link diagrams to visualize a subset of their dataset as sanity checks to make sure that their KG is building properly. However, 12 of our participants reported scalability problems for end users. For example, in the image to the right, if there are too many nodes and edges on screen, it can be difficult for end users to digest any meaningful information. Also, some generic node link diagrams may not be domain-specific enough, which we will talk about later. Many participants found that KG consumers end up preferring simple tables rather than trying to understand what's going on in the ball of yarn. This is from P12. They said that we put a lot of software developers' efforts into this GUI that showed our analysis as a graph to the end user. And so they had experimented with changing the colors and the shapes of nodes, changing the way that lines were drawn, with zooming in and zooming out features. But in the end, the results that always came back looked like a ball of yarn. They were unstructured and really bad. Users could not make sense of it, and in the end, they preferred a table. Another participant said that in our experience, the more we can shelter the end user from the underlying graph structure, the better their willingness to interact with the data and accept the results that come out of it. As soon as the level of a complexity in the graph reaches a certain level on screen, users really tend to shut down and not trust any of it. Now we will talk about visualization opportunities we identified. In general, we were not able to identify any single solution for the best visual encodings for KGs, and we instead identified shortcomings of current designs. Our participants told us that many visualizations will probably need to be domain-specific and tailored to the needs of the end user. We will suggest a variety of visualization research directions, and this opens up research directions in curating KG task taxonomies and potential KG design spaces. Some of our participants advocated for visualizations that abstract the graph away from users. You'll remember that one of our participants found that end users preferred simple tables instead of complex graph visualizations. Under the hood, the end user doesn't necessarily have to know that the KG is there, but they can still get the benefits of the KG with improved results. And that might be the most effective way for non-technical experts to engage with KGs, rather than interacting directly with the ball of yarn node link diagram visualizations. And here's a quote from one of our participants: "Just because you have a knowledge graph doesn't mean the visualization itself has to be a graph." Some of our participants stressed the need for visual solutions to balance digestibility and discoverability. Graphs have a strong advantage in that they can make it easy to discover and explore the data by traversing the links to hop from node to node. But they can be difficult to digest in the case of node link diagrams. Some of our participants really liked using Wikipedia as a kind of visualization tool, in which Wikipedia lets you read and digest information about a particular node, but then discover new articles or nodes using the hyperlinks. Related to that, several of our participants advocated for using baseball or knowledge cards similar to Google or Wikipedia. Instead of showing everything about the node, you only display some high-level important information dictated by the data domain or context. Here we have an example knowledge card of a cyber vulnerability displaying important CVE identifiers, affected hardware, and related vulnerabilities. Other opportunities we identified for KGs include using them for explainable AI systems, developing interim query builders to help users get results as the system is trying to find data for the query, using KGs for timelines and temporal tracking, and also developing schema enforcers and builders for KG builders. In conclusion, we interviewed 19 knowledge graph practitioners to understand their roles, visualization needs, and future research opportunities. All of our